Fantastic. Hey, Molly, Adrian, thanks for setting this up. Chris, we appreciate y'all. Just to expand upon what Ryan was basically saying, if you can see my screen, so we are an engineering company, we're in Temple, that's where Houston, where Toby is. I'm down in Sugar Land. So we've been in business for about 30 years. Toby and I have been working together for about 22 of those. And as Ryan said, so we're an engineering company, so we do CFD, computational fluid dynamics, so the flow of air or water. So we've actually done some things with Speedo for their goggles for swimmers. That was quite an interesting thing. We did some things for Nike also. You can see the flow across that car. FEA is simply when will something break. Everything always breaks, but we can tell you when. Then we do mechanical design. About 10 to 15 years ago, we started selling 3D printers also. So we use them in our engineering work to prove out the designs that we're doing for customers. It's easier for a customer to have something in their hand and to realize the form, fit, and function of something versus just showing it to them on the screen, whether it be in a 2D or a 3D. So you see FFF over on the left. Most people would recognize that as FDM, fused deposition modeling. So since that's a coined term by a manufacturer, we've had to shift to FFF. Basically, I'm going to be very elementary. It is almost like a glue gun like you've used, and it lays down a layer, the bed drops, and then lay another layer down. Okay, in this particular case, the orange is the model material and the white is the support material, because obviously I'm building plastic, I'm building layer by layer. And as you can see, the trigger of that gun, it needs something holding it up for it to build another layer. I grew up in Minnesota, so we used to build igloos this way. So SLS is a powder-based system. We'll talk more about that when we talk about the HP. SLA is more of a vat, so it's a liquid. And so it uses either laser or light to go ahead and cure everything. And DMLS is direct metal laser sintering. So I'm actually using lasers to fuse together metal particles. All of these have pluses and minuses. What we want to key up a little bit is this is not a pitch to HP. We are a reseller of, as Ryan spoke about, of a number of different technologies, but this is one that we are utilizing in a lot of different efforts at the moment. And so Toby can get into it more later, but we have a processing station on the right. We have a build unit that goes back and forth between the printer and the processing station. So it fills it, it prints it, it brings it back, it cools it, recaptures its powder. This was an example. So where you basically say, where does 3D printing come into play versus typical plastic injection molding? This was a customer that was in Austin that needed 100 of those parts, and he needed them quickly for a thing that he was doing for Home Depot. And what that was there's actually circuitry inside there, and it puts it on the display at Home Depot. So as you walk by it, it reads your smartphone, your Fitbit, your smartwatch, anything it can. It tries to figure out who you are, how long you stood in front of the display, if you walked by it, how long it took you to come past. It's very interesting and very scary, big brotherish at the same time. But so he says, hey, Kelly, I need 100 of these, and it's going to cost me $2,500 to get a mold from China. And this was pre-corona PC, and it was going to take him 8 weeks. And we said, we'll just print it for him, and we were able to get them to him that afternoon. So there's the advantages of 3D printing. Is 3D printing the go-all for everything? So in the age of corona, we're having to make 100,000 masks. Probably not. It's make a mold and go on with it. Toby, you want to jump into this section just real quick?
So in theory, you conceptually think of designing parts. So if you were traditionally doing an injection molded process, you would always constantly have to think about constant wall thickness, pull direction, how the manufactured part's going to get out of the tool per se. So talking about adding draft, et cetera, and so forth.
Toby, let me know when you want me to
What it
change
is
next.
referencing is you can think in print utilizing a 3D printer. You have the ability to go non-traditional compared to injection molded process. So you could core out additional areas. You could have undercuts, stuff that typically would cost you money in an injection molded process. So creating slides, etc., threaded surfaces, all of that can be done a little bit differently now that you can design for additive manufacturing versus designing for injection molding.
Let me know
Go
when
ahead,
you want. Next slide.
Yeah. So ultimately, with HP, this is looking at the HP production system in a little bit more wider range. What this particular slide is talking about is in every project, there is an opportunity. Now, that opportunity may be for injection molded, it may be for a sheet metal part, CNC. There's an opportunity for every type of part. So what drives that opportunity? Typically, it's how big is the part, what type of accuracy is needed, and what type of mechanical properties are needed. So that's where that middle section of this concept comes into play. So if you know the part size, the mechanical properties, the dimensional accuracy that you need, you have the ability to further channel or narrow down what technologies can be used. So typically in a non-design for additive manufacturing application, so we're talking about injection molding aspects, there is a break-even point where you have quantity and you have a price of a mold. So if the mold is super expensive, but you need low quantity, it doesn't necessarily make sense to make an injection molded process. You may go to a CNC if it's possible, so forth and so on. Go to the next slide, Kelly. Where design for additive manufacturing comes into play is we use that same criteria when we're talking about, we know the mechanical properties and we know the part size, the quantities that we need. We can design for additive manufacturing based off of those particular applications. So there are various different printers. HP is just an example that we talk about where it can print in nylon. So nylon's a pretty robust material as far as chemically reactive and stuff that it can be used for. So knowing that, that's good. HP has a larger build volume than most 3D printers. And then part accuracy is very important, and HP can attain very accurate parts. So with all that in that application, you can design for 3D printing. So you open up that middle section of the slide theoretically, which is a trickle-down effect. So if you can now produce more parts utilizing designing for additive manufacturing 3D printing, you have the ability to change manufacturing in general and widen that process of time to market. Make the printer work for you. So if you're utilizing traditional manufacturing, injection molding, if you've ever heard of creating a tool with multiple cavities so you can produce multiple parts at one time, that theory can be used inside of design for additive manufacturing. And on the left-hand side, they use something called a nested structure. So you design to accommodate that nesting structure. What you're kind of not seeing on the slide is imagine that particular structure had straight wall, vertical walls. If it had straight vertical walls, we would not be able to nest these because we couldn't put them on top of each other. They would have to have that spacing. So what we were able to do when we designed for additive manufacturing is simply slope the walls, and then we can get those to actually compress down on each other a little bit, which in turn gives us more parts per build. Again, reducing the total cost. Another application is the tessellating patterns, where they're simply taking one part and they're able to flip it 180 degrees in order to utilize the full width of the build chamber.
Toby, I want to point out one thing in that thing on the right. What's happened though is with additive, with 3D printing, you're able to take away a lot of that material that's on the inside. And so anytime you're trying to fly something, weight is always a huge factor, whether it be just drones or in space. I don't know if you want to key up on that at all.
Yeah, so I mean, ultimately, with design optimization softwares that are out on the market, we're able to structurally keep it as sound as possible, utilizing different forces applied, so forth and so on, and able to reduce the weight. And sometimes the way that those design optimizations work, it reduces the weight, changes the profile to where it's non-injection moldable, or it's injection moldable at a higher cost. So again, one of the benefits of design for additive manufacturing is being able to use that technology that we have today to produce parts that are structurally sound but lighter and cheaper. So the drone that Kelly was talking about earlier, you can visually see that now. So there are a mixture of 3D printed parts and then also purchase parts such as motors, batteries, so forth and so on. As he did mention, all of this was printed at one time. So we were able to print all the 3D components that we could at the exact same time through the nesting process. So you can see that some of these parts would fit within others when we were talking about printing the nested parts. Notice if I can get in close enough, it does have a texture. So we were able to print 3D textures as well to be able to see that if any texture is needed. Another application that Kelly spoke of is being able to utilize the full size of the build chamber and then glue multiple parts together. So the red BOP that you're seeing here is roughly about 24 inches from handle to handle, of course, which is larger than what we can produce at one time, but we're able to produce sections of it at a time and then go through a gluing process, or sometimes we can utilize off-the-shelf hardware so we can screw items together. So with that functionality, we have the ability to produce much larger parts. Now, this particular part was printed utilizing what we call the natural gray color, and it was taken to a body shop and printed utilizing automotive paint, just as an option. All right, so speaking of color and how all this particularly works, a different alternative is utilizing HP's 3D color printer. Now, I'm going to talk in general at first, and then we'll talk about each individual system. So as Kelly mentioned when he was talking, it is a powdered-based system. So it utilizes a white PA12 nylon powder. So regardless of which system that I'm going to show you, I'll show you two different ones that HP makes. They utilize a powder-based system, and then they apply agents that underneath heat will bond the particles of the powder together in order to form your 3D printed part. Now, if I take a step back, this particular machine is HP's 500 series. So this is a 580. The 580 produces full color parts. There's also a 540 version, which produces white parts. So this 580 version was able to produce all these different scenarios. And I'll talk about how it actually does it layer by layer here shortly. So you can see that it can produce very vibrant colors through the process that we utilize, and then additional processes such as smoothing through our AMT process. So it can produce solid particular parts like you see here, or it can produce very thin parts. So here we're talking about 80 thousandths wall thickness. And then some parts of the particular flower are even thinner. So the way that this particular process works, I'm going to move some of this stuff just so I can demonstrate a little bit more. Again, this is on the 580 version. So this particular build chamber, Kelly, I believe, is 13 by 7 by 9. Is that correct?
That is correct.
Okay. So that is the build plate that you see there. So it is currently recessed, but your powder would fill on this particular build plate, and it will produce or build layers one at a time. Print heads, which produce the agents, come across the powder, and as they come across the powder, they spray agents where your 3D part is located. And then it goes all the way back. Now, during its back process, it produces heat, but the heat comes from a secondary unit, and that secondary unit is this fusing assembly. And the fusing assembly actually produces the heat. So as that agent is laid on the powder, this particular assembly comes across applying heat, which is fusing the agents to the powder and producing your part. So it's a very simple process, again, utilizing powder, agents, and heat. So it's not much to it where it utilizes the bulbs. It's just all that proprietary agents that HP uses to bond everything together. So it's a wash, rinse, cycle, repeat type application after it produces heat. Another layer, the bed drops, another layer of material is applied, it's flattened out, print heads come back across, applies agents, and then the heat comes back and goes about over it as well. So again, all of that is done through the software. Everything as far as you take your 3D part, put it into the software, it produces your 3D part. Not much different than any other application. Again, this is just their powder-based system. Any questions with the color concept before I walk you over to the larger production HP machine?
So Toby, from start to finish that, well, Molly unmutes everybody if they have questions. Start to finish for that size is completely 18 hours. So from it heating up to getting your parts out, it's an 18-hour period, correct?
It can be as low as 16 hours. There's some stuff that we can do with the software and print profiles where we can get it around 16 hours. That's from the time you hit the print button, prints the parts, cools the parts, removes all excess powder, and you're able to get the parts out.
And since we're sweeping across in the X, Y, the Z is what's taking the most time. So if you were to be doing only a half a build, or what you typically do in your engineering process, you will print something for 4, 5, 6 hours in the morning. You will go in, clean it up, and then you'll build a full build at night. So the printer is being utilized in a kind of 2 shifts, 24 hours a day type of effort.
Correct. And one other thing to just add on and clarify before I show you the other machine is this is an all-in-one system. So you print your parts get picked up out of here. There's no vacuuming as far as the excess material. The machine does all that for you. The reason I'm bringing that up is when we go to the production machine, to make it a production unit, there are things that they did to change that process, and we'll talk about that. All right, no questions. I'm going to walk you to our room that has our production machine. I am going to show you through the window, and the reason is the machines are running, so it's a little bit, it would be louder for me to talk over the machine. So I will go in there, but I will mute myself. And if Kelly, if you want to talk any more about it,
yes,
you can do that. But on the left-hand side, as far as what you can see on the screen now, is the printer itself. Trolley being in front of it, and then processing station, which is where you go in and actually evacuate your parts. Now, which makes this a production system is once the parts get printed, they would be located on the trolley. All of your parts can come out of the printer and they go inside of the processing station and they're able to cool. So the way that HP system, production system works is if it takes 12 hours to print, it needs at least 6 hours to cool. You do have the option to let it naturally cool. So naturally cooling is basically what's taking across, and that card over there, you can see that it has material on it. So there's material and parts inside of that particular powder, and we're letting it naturally cool. So the naturally cool process, if you're worried about mechanical properties, to attain the highest mechanical properties, or if you have very thin parts, We typically will let them naturally cool so they can cool to the environment. And then we would go in, take them to the processor and evacuate the material and go in and pull our parts out. This particular unit does utilize recyclability concepts. So with that being said, the powder that it prints in is 80% recycled and 20% virgin or new material. And you're able to recapture about 95% of the material that is not printed on when you go to evacuate the powder after printing. So it is a great concept, and it is different than a lot of other technologies where you typically would trash used material, or in an FFF type scenario or an FDM type scenario where it utilizes supports. All that support would be ripped off, taken, and trashed, so you lose material. In this HP process, we don't have that. We're able to, again, recapture about 95% of all the powder that is utilized.
Toby, I'll take over the video, or I mean, I'll take over the audio if you want to go in there. So what Toby's talking about as far as recapturing the support, you remember the orange gun, that orange material is a model material, but all that white was going away. So what he's fixing to show you, we're going to kind of zoom in and show you as best we can the sweeping process, similar to what he was demonstrating by hand, where you have the powder being laid down, and then you can see the light coming on, and it's doing the fusing. That coming north south is the powder. It lays a layer, it goes back, it sprays agents, and it just continues in that effort after. And you can see some of the parts that we're making, and you can see the powder, the Archimedes screw depositing another layer, and then it sweeps across and lays it down. Toby, let's move over to where the parts that are coming out of the processing station, if you can hear me. So we've been doing some things for the medical community. We're working with a group up in North Texas that they're doing a hood type ventilator. So you can kind of see the powder that is where it's coming out of the processing station, and what we're able to get done. So this is just a powdered nylon. Once it's cooled, we can get these parts out, and they get blasted in a sandblaster, and then from there, those are clips that are holding the helmet, this big plastic helmet, down to a base for people having to go for COVID support at the moment. What's on your left, Toby? So there's a bunch of those clips that are coming out, and the rings for the more parts of the helmet. So basically what Toby just kind of showed was, and we're going to go over it briefly, was we're laying down the powder, it's sweeping across, it's laying down the agents. The black agents that they show on there are the fusing agent. The blue is a detailing agent. We're applying energy, and it's as you can see on the far right side where it's fused, that's because that's where I am laying the fusing agent. And then I lay another agent that is giving me a crisp edge. So that's that part in blue. Toby, you want to add anything to that?
No, you did good.
Okay. So just some rough examples. So here's where Toby talked about design for additive manufacturing, 3D printing, and how you would utilize it versus, say, traditional manufacturing. So we don't have anything against traditional manufacturing. Plastic injection molding, NC, they will always be out there, and we love them. We kind of offer a hybrid, and HP went ahead and said, you know what? It's kind of weird, but we are going to print our own parts that are going in our printer. So the child-parent relationship gets interesting here. But some of these parts, they are able to print that they're not able to manufacture very well in a traditional sense, and to go ahead and save some time and money where I'm printing a complete assembly. versus printing things in multiple pieces and then assembling them. Toby, you want to comment on that?
No, that was pretty good.
All right. So here's a good example where how you would do it in a traditional, where you're having to do multiple molds, versus I'm able to just print this in the HP printer one time and get a great process. Where, because they're not making the printers that we've showed you, they're not making tens of thousands of these every year. We're talking about a lower quantity, and that's where using additive manufacturing can come in. Toby, I'll let you take this one. You're good at this.
So go back one slide. I want to add something else on that.
Sure. Sorry, I was taking a drink of water.
So this particular part is part of the 580 printers, so the color printer that HP produced. But what took place is during the beta testing of the machine and so forth and so on, they realized that they needed additional air duct for flow purposes. So this is where this part came into play, and traditional manufacturing is where they wanted to go with this. And when they came back and said that it's going to delay the release of the printer by 12 weeks, they went back and said, we've got 3D printers. We know what the design for additive manufacturing is. We know volumes that we need, structural aspects. They were able to take all these individual parts that they were going to have traditionally manufactured, combine them into one, as Kelly mentioned, and able to produce the part and keep the machine release date on schedule. So it's always keep the additive manufacturing world open. Doesn't matter if it's FFF, SLA, whatever it is, keep it open and explore all options. All right, Kelly.
Toby, if you follow me on, well, I click down, if you follow me on LinkedIn, you notice that I posted something that a guy took apart at Tesla the other day, and on the HVAC system, it was all plastic injection molding except for one part, and they're not really sure what Tesla was thinking, that it was 3D printed as an add-on.
Interesting. Okay, so this particular part was actually used on another line of HP printers. It's kind of hard to see, but on the far left-hand side, it was an aluminum machined part. And all it did was held the print head carriage. So what they did is they said, well, instead of using traditional manufacturing CNC it out of an aluminum block, let's go in and print it as just a 3D plastic part. We know the structural components that are involved. We can run FEA based off the design, so forth and so on. So they were able to reduce the cost in that initial run by 50%. So they then said, well, we have different softwares that are available to us. We can go in and do a lightweight design. So instead of having that big block, they went in and punched holes or diamond patterns throughout all of that. They were able to reduce the weight by 93%. And then all the way on the far right-hand side, utilizing design topology design optimization. If you know the forces that are applied to certain areas, utilizing softwares that are available on the market, you can go in and have your design be tweaked to where you're removing all unnecessary mass or volume in order to produce the part. So if you look at the slide starting from the far left-hand side, it used to weigh 355 grams, and they were able to get it down all the way to 23 grams. And they saved a significant amount of money, and they also changed the carbon footprint that particular part made.
And then one thing, Toby, I want to key up on the carbon footprint. So if you are trying different things, and so rather than shipping parts all over the place, we can do just-in-time manufacturing, and we're shipping things digitally, and then they're being 3D printed additive manufacturing at a facility. And so again, there's a carbon footprint reduction.
So this one here is just another example of taking traditional manufacturing on the far left-hand side. So these were all machined out of aluminum. It was very various different components. I can't read that, Kelly, but I want to say that it was around $450 to
That is
produce that
correct.
assembly.
Yeah.
And then on the far right-hand side, they changed it for design for additive manufacturing. So ultimately combined them all as one part. And from that, they were able to reduce it under $20, I believe.
Yeah, $18.
So it's taking what you're traditionally used to doing, knowing how that system functions, and being able to design for additive manufacturing. Again, whatever that process may be, MJF, SLS, or FFF. Okay.
I think we kind of covered a lot of that. So we've been talking about the HP 300, 500 series, but again, this is more of a talk aimed at kind of design for additive manufacturing, 3D printing. So here's a part that in the 580 that Toby was showing, you can see kind of the size of it based on the hand, that I think we were able to make, I believe, 50 of those in 16 hours, Toby?
That is correct.
And now the beauty is not so much that we can make 16 in a given, or in 50 in a given period of time, but the beauty would be that if those were different and say they had names on them. So say one had Molly, one had Adrian, and that can be either embossed or embellished. So that's where the being able to make changes or print different things all at the same time. So this is a Xrize. It's another one of our machines that we have. This is a color printer. So similar to the HP, less in cost, a little less build size. It's a FFF type situation. So again, you can see what it is that we are currently building. You can see the time that's on there, and that's kind of a freaky head, but that is something that we built the other day. I believe that took in the magnitude of I think 25 or 30 hours, Toby. But this is a office type printer, where the other one we have in our office, but this one weighs 120 pounds. The other one that Toby was shown, that HP, weighs 2,000 pounds. So you can see that basically it is going back and forth like a fancy glue gun that we spoke about. And then that bed just continues to drop in another layer. So, you know, like regular FDM style printers, this one has print heads that we can actually print the colors and ingrain them into the print also. So this one is in the 50,000 range, where we were, and that other one we were in the 150,000 range. So you can see the inkjet cartridges that is using. And then Toby, if we open up the other side, we'll see the spool. So typical, and that has two spools. So as one runs out, the other one. So it looks like weed eater line, frankly. And there's the excess and that waste right there. So yeah, so we're going to show metal real quick. Again, this one's not running at the moment, or not doing anything at the moment. It is running. It is an FDM style also. So but instead of that weed eater line like Toby had showed you before, he's going to go ahead and show you that it kind of looks more like a straw, a solid. The gray is the material, the white is the ceramic interface, because I can't print metal on metal. I have to have something in between, otherwise we'll never get them apart. So as Toby looks at the machine, as he lifts up the top door, you'll see where those rods actually reside. So we can print stainless steel, 17.4 3/16, and then those ones on the right, those where the ceramic, those white interfaces come. So it comes, and those are the different, we have 4 different materials that are out there. 625 and copper are coming out later this year. And so it prints it. It is that metal rod that he showed you was a powdered metal, a wax, and a polymer all combined. So we're not really melting the metal, we're melting the wax, and the metal is just kind of flowing along in the channel. But we have to get rid of that wax. And so that next piece that Toby is fixing to show is what's called a debinder. That actually takes the wax out of the part. And then once we're done with the debinder, then the furnace, and this is all office friendly, the furnace then extracts the rest of the polymer, and it shrinks the the part down to the size you want. So again, so whether it be, okay, we can talk about fiber also. Oh, there we go. There's some good metal parts. Toby, you got anything that's secondary machined? Okay, so we're talking about, this is more like a cast part that when it comes out, but you are able to secondary machine it, so you can see that we get the face that you wanted, and then you can also we have a process in Brian called REM that it can go through a slurry and polish it up so it looks kind of like a snap-on tool. Toby, why don't we go jump to the fiber real quick, and then we'll wrap it up with questions. So the fiber is by Desktop Metal also, even though it is they have metal in their name. So this is a different process that it can do peak and peck for high temperature. It can do carbon and fiberglass inserts and reinforcement, and it can also lay down a 3 millimeter automated fiber placement tape for strength. So if you're familiar with on the aircraft, you might see large, we'll talk about that part in just a second, you might see large fiber placement on fuselages and things of that nature. That is actually a vent that comes from the front of a car to a BMW race car and blows air onto the brake rotors to keep them cool. It needed to go up to 250C, which is about 480F. And it's very lightweight, it's very durable, it's very strong. What's interesting about these printers is it is a subscription base, so it's 3 years at as low as $3,500 a year. That shark fin thing is interesting. That is actually the bottom of a surfboard. So you would have 3 or 4 of those on the bottom of a surfboard for controlling. And I'm not a surfer, but that's from what I understand. The T-Cross, Toby, I think is off of a drone, if I remember right. Also, so very lightweight, strong but flexible at the same time. So it's a nice printer if you need the strength and you need the high temperatures.